All right. So today I'll be talking a little bit about the research that Google has been doing in terms of streaming 6 degrees of freedom video content. And specifically, researchers from Google has developed the first end-to-end 6 degrees of freedom video system that can stream over internet connections. That is, provided that you have a 1 gigabit connection. Now, we're all familiar with a ton of like 360 videos that are available on quite a few different kind of platforms. We have, for example, 360 roller coasters, horror experiences, vlogs, gaming videos, all kind of different kind of content. And the idea of this sounds quite awesome, but as soon as you try it, you do feel a little bit disappointed, especially as a VR veteran. And the question I kind of want to answer with this little science section is why is that? Rather than going into like the technical specifics of how Google managed to get around this. I will briefly touch on this and try to explain it in a rather simpler manner, but the overall focus will be, why does this happen? Why does 360 video not feel as awesome as you would expect it to do? And part of what makes our visual system so effective is that our heads move and change our perspective. And this then allows us to feel a certain sense of depth through something that is called the motion parallax effect. And this is something that is called a monocular depth cue that causes objects that are closer to you to appear to move faster than objects that are further away. And the further away something is, the slower it appears to move. We all know that when we see a plane, we see it moving rather slowly, but that is because it's so far away. And that is a kind of a cue that we get of the distance that is between us and that particular plane. That is also the reason why you're sitting in a train and you see it moving next to you, that you assume that there is a certain speed that you have yourself. That's also related to that. And also, moving our head allows us to see how light interacts with the surfaces in the scene, which then gives us information as to what particular materials that the scene is made of. So for example, we get a perfect reflection that we know that it's a metallic surface, or if it's a rather imperfect glossy reflection, that is a different kind of material. That is, by moving our head, we can see the reflection change in that, and we can get some information on the actual material. Now, up until now, what most of those like 360 and 180 videos have been doing is like only allowing us to see from a certain viewpoint. But this viewpoint cannot be altered regardless of how the user moves its head. And this is not really comfortable. It can cause not only like messing with your visual and vestibular system and cause motion sickness, but that can affect a lot of people in different ways in many kind of VR headsets. So they've been trying to find ways around that, and one strategy is to get around this is to use a multi-view stereo camera or depth sensors to estimate the 3D depth of the scene in each direction, so that the panoramic image can then be reprojected with image-based rendering to a new viewpoint. A drawback of this is that, unfortunately, it looks rather dull. That the scenes are not typically well preserved. You have disoccluded areas around object edges, and it's very difficult to fill this in very accurately. And furthermore, because you have reconstructed 3D geometry, it can be displayed with textures. This fails to reproduce a view-dependent reflection. So you don't get really a sense of material, which gives everything a rather like dull reflectance. Now, a different strategy is to record a sampling of the light field using an array of cameras that are distributed across a surface. When used with modern interpolation techniques that include per-view depth estimation and view depth texture mapping, these view-dependent reflections can be preserved. So you do get a very accurate kind of reflection. However, unfortunately, there is a very associated complexity and associated costs with that, with these denser camera arrays and sparse samplings that are prone to noticeable edge artifacts as well. And none of these strategies have ever been paired with an efficient video compression scheme. And then Google comes along and decides to like get involved in this as well. And what they have done is devise a solution that includes capturing, reconstructing, compressing and rendering a very complex scene in such a way that it can be streamed over a 1 gigabit connection. And it's especially that last part that is a very impressive feat, mainly because of the insane quality that they can achieve despite the compression that they're using. So now we'll go a little bit into more technical details of how they managed to accomplish this. It is rather complex, but I'll try to break it down on a couple of points. So first we have the cameras. They used 46 4K cameras that run at 30 frames per second. They're roughly 18 centimeters apart, and they have a field of view of 120 degrees by 90 degrees. These overlapping field of views then allow reconstruction of near field objects of up to half a meter. In the paper, they even describe up to 31 centimeters. And that is only a roughly estimated cost that was provided by Upload. They did the calculus on that. It was roughly $7,000, which is quite cheap. That is roughly the price that the guys are paying me for doing this episode on the science episode. Then what they did next was they performed a view synthesis that they used to something called the deep view method. That is the kind of algorithm that they tried to use for this. But they replaced the multiplane image with a multisphere image that encodes a concentric sphere, a set of concentric spheres with RGBA textures around the viewer. Now, due to the enormous amount of data that is in such an image, this is obviously very challenging to compress. So what they did is they reduced these multi-sphere layers to 16 layers meshes that conform to the layers in the scene. And then in the final format, what they did was they took these layered meshes and grouped them into small spans of time. The 16 layered meshes textures were combined into a single atlas. And this atlas is then compressed with the standard video codecs that we all know, while the geometry of the scene is stored as, the geometry of the texture is stored as a separate stream, which is a very common thing to do in gaming as well. Now, the most impressive visual thing is the composer depth visualization that they managed to accomplish, where they showed the tree branches, showing how the colors of even the thinnest branches seem to change as you move closer or further away, which I think is a very impressive thing. But overall, they managed to succeed in generating a 6 degree of freedom volumetric video, so you can actually change your viewpoint while you're looking into the scene, up to a fairly decent distance as well. It's a 70 centimeter viewing baseline, so that means that they have an overall of a little bit more than 180 degrees of field of view, and they have a 10 pixel per degree angular resolution, or as I like to call it, very, very cool stuff. So yeah, that was it, what I kind of wanted to highlight. If you guys have any questions in the chat, like, be sure to let me know. Just tag me in there, and then we'll try to discuss it.
Yeah, like when I first saw this, it just completely blew my mind, and I thought this would be great for you to try and explain, because, you know, Nathan and I have dabbled in like VR 180 content, VR 360 content, and capturing it, and you're right, you know, when you view it back, there is some depth to it, but you have to keep perfectly still for the magic to work. The second you move, the illusion is broken, and that's basically what they're addressing here, right? You know, you're going to be able to move your head, 70 centimeters roughly, in different directions, and get that perspective.
I don't know if it's exactly 70 centimeters, but there's certain like a range of movement that you can have that is a very comfortable range.
Right.
I know that the 70 centimeters, I don't know exactly what that refers to, because they kind of use that as a way of giving like the total field of view that you have.
Yeah.
But it is very impressive, and it looks very natural and very comfortable as well.
But I think you're right, you know, even just that little bit of movement, even if it is just a little bit, you know, it really adds something to that experience. And you hit the nail on the head with motion sickness as well, because that's one thing, especially if you're watching like a roller coaster in 360, which I don't recommend you do, by the way. But as soon as you start moving your head around or trying to anticipate the corner of the roller coaster or stuff like that, it just completely throws you out of whack. So this is going to be super interesting.
Mm-hmm. Yeah, and especially because the technology that they managed to devise is actually on the cheaper end of the spectrum. Of course, that is only for the actual equipment, because there is a major caveat with this kind of research, and they even highlighted in the paper themselves, is that, I'll quote what they say. They say in their own paper, a drawback of our training and processing pipeline are that they require substantial cloud computing resources. It would not be practical to process a several minute long video on a single workstation using our current framework. And of course, because they have the backing of something like Google, which is a giant computing platform in itself, just because the cost, the hardware cost, or the computing cost of making a scene like this is incredibly high. I don't even know how many terabytes or whatever that they're using in order to generate something like this. But that is, of course, something that you need to keep in mind in order to make a scene like that, is that there's an enormous amount of machine learning and compression and these kind of like algorithms that need to place in order to make this scene visible in the first place.
I had a question about the data throughput you had. You quoted a gigabit per second. So does that involve any protocols that would intelligently note where your head is in that space, and then basically you're only sampling from the data available at, I'll call it the server end, then gets piped to you as the client? Because I'm thinking that like the latency time, between me and even North America is, 200 milliseconds or something or less. Why wouldn't they go for, instead of sending you all of that volumetric data together, and choking the pipe, so to speak, with this 1 gigabit, like, is that already the compressed figure, or is there any mention of a protocol that
is the fully compressed figure that they're sending? But it's not your head movement that is being sent back. So that is not the case. So you actually get the full video stream because they eventually compress it to a general codec.
Yeah.
So it's just like a regular kind of video that a 360 video that you would watch on YouTube. And they even managed to do it on web browsers as well. So you can also use it on web browsers to give the input there. But you get the full image format sent to you.
So the tracking is handled locally. The head tracking is handled locally.
But that's what I was saying. Like, why wouldn't they choose to push that down the other side of the protocol? So I get what you're saying, Rowdy, and that's what I took from your explanation. The only thing that I missed in the explanation, you mentioned the word atlas. What did you mean by atlas? I didn't understand that.
What they mean with that is that what they basically is they use all of the textures and they combine it together into something that they call is an atlas. So you have, because it's a machine learning algorithm that they basically apply in order to reconstruct the image. Because of course, when they start out with this original video source, the data is enormously large. So what they do then is they try to compress that. First, what they do is they select a certain amount of data. So they take the 16 layered meshes and then they compress those layered meshes and they separate the textures over that into a different file format or stream format. And then when you pull those together, you have that atlas. I believe it's the atlas that then goes over what you're trying to see.
Okay. Yeah. Okay. So it's kind of like
the atlas stores the textures.
Thanks.
So
that's helpful.
The video needs to take it from the atlas in order to display.
There's a good question in the chat. They said, is there any content that we can watch right now, or is this still just in the experimental phase?
I haven't. I mean, they did show a very nice video where you can explore it yourself. I haven't found any specific content as to where I can like try it myself already. But I guess that's like a matter of time. I think this is more also like a proof of concept, and they still have some points that they want to improve. Like for example, they want to improve the latency also because they used a fairly cheap kind of thing to put the cameras on. The sync between the cameras is not completely perfect, so they still want to improve on that to get but in the end, like the overall result is so much better than the other methods that are available as well, and so much cheaper that I do think that they'll continue with this research, obviously, but
this would revive the 360 and also 180 platform in a new way, because this sounds way more immersive than what
the only problem is, like I said before, this is not something that you can easily do at your home, even if you had 46 4K cameras, and that's a little bit the issue with this, of course, that you need to have the computing needs to be done off source, because I don't think anybody here or anybody has this kind of computing power in order to do this in a reasonable amount of time.
But Rowdy, is it better than a G2?
Barely.
Barely. I thought so. Yeah. No, someone in chat, Terry, mentioned. Thanks, Terry. Good comment.
Yeah, 46 4K cameras.
It's hard to think about it. But the nice thing is that I love when scientists are trawling at a problem. Scientists and engineers are just like clawing through it, like we're gonna get there. And then you know what's gonna happen is someday this will be easy somehow. Like they'll have gotten past these barriers, and we'll have that. We'll have the ability. Like for me, it's super exciting. As somebody who's been streaming VR games for 6 years, I'm like, okay, this is something that's super exciting now to me, because you could have someone jump into that platform that we've always wanted, which is, jump in and actually kind of experience the same six-off that the player is seeing, even if it's only in a limited range. And that was the main thing I took from your explanation, which is really exciting, because you're not trying to, light map and, rebuild the entire scene and calculate every possible angle. You're actually just saying, give me a degree of flexibility around where the viewer is and allow me to, have my normal head motion, not that I'm just, let's say watching Mike and strapped to his body as he's moving his head. So it's great.
Yeah, and the nice thing about this as well is if you look at the paper yourself, they've done a really nice background of the research. So how they got the idea and like where it kind of started, because of course it is not the work only of Google. There's been a lot of people before that have been investigating this technology as well, and they kind of build onto that. But it's a very nice kind of overview that they give in terms of like the background of the research. Also, I'll make the presentation. I'll make this available on my GitHub account. I'll post this in the link down below, so you guys will find a reference there to the actual paper and to the presentation.
Nice. I think it's fascinating. It's kind of like the basic brute force approach, like Zim said, and then you're going to see this be refined and refined and refined over time until something's going to be super convenient and unique, and it's just going to do it by the click of a button sometime in the future.
And then we can ride roller coasters again without getting motion sick.
I just think it'd be really neat when you have this ability, even if it comes in like highly compressed, like even if you had a video image that wasn't super clear, but you could move your head around that, it would just feel really natural. And I think it would sing with your kind of, again, your human brain in that environment. Even if it was like, do you guys ever remember like watching your first 360 video or your first 360 experience in a VR headset? Like I remember doing one with a hot air balloon, and I was like, oh man, you can look all over, like this is pretty cool. And then I remember watching, I think it was Remarcus's like 180 video, and then watch some of your guys' stuff, and it's like you can see where it's going, and it's definitely not there yet. It's like
I think
there's
the
barriers.
biggest potential for this kind of technology that they've developed right now, it's mainly in like sports, where if they would place a system like that, which is actually not that expensive then. And if you have a major brand that is doing it, they probably also have access to like some Offsource computing platform to actually, of course, not in real time. I don't think we're there yet. But if you could record matches like that and have them played or like experienced in a way afterwards, I think that would be epic.
The way I see it in my mind as well, just imagine if they combine this with like volumetric capture, where you could move around like nodes in a volumetric capture, and then in the static nodes have that kind of degree of movement. That would be really cool as well. So very, very exciting.
Nodes with 46 cameras. So that's
just give me the front row seat.
Petabytes of data. Yeah, exactly.
Watching a movie with this stuff for 2 hours and really being in there and looking around stuff.
Yeah,
that would be amazing.
And on my dial-up connection, I'm sure it'll work great.
But like that's interesting. You guys are like, Nathan, you just hit on a really interesting point there. So what if you were looking to just augment that experience that we currently have of being in a virtual cinema, right? You just want to feel like you're sitting next to somebody in a cinema watching a 2D film or whatever. Does that strip out some of the complexity? Because if you're not looking to transmutate like all of the scene or a detailed object and all those scene details that you talked about, Rowdy, and you're instead looking at some basic content, but you still want that head movement freedom, I'm wondering if there's like a halfway house here that maybe we would see sooner. Someone
I don't really understand what you mean. Do you mean that when you record in a cinema, the movie?
So if you're sitting in a 3D movie like RiffMax Cinema or Big Screen or something like that, you're sitting there, you can watch content that isn't VR content, right? You're in VR, but you're watching something that's flat or whatever. And the environment that you're in, like Mike's to my right, Nathan's to my left, right? I'm in this like hamburger, this alien hamburger of F.Reality, and I'm trying to just get the sensation that what Mike mentioned. At the moment, you move your head in one of these streams, right? And it's 3DOF, and the second you move your head, you've noticed that it's not full 6DOF. It's not true, right? Is there a way that because of what you'd be monitoring isn't interactive in a 6DOF way, and your mechanism of tolerance is like quite constrained, would that help at all? I'm trying to just think it through there.
I would still think that, like, for example, if you would do some photogrammetry into that movie theater and then just play, like, cut out the screen and play the 3D movie on there and rebuild the screen in VR, that would be computationally way less expensive instead of recording in there.
That's what, because what they're trying to achieve is that full volumetric presence.
What they really did was like very complex scene, because they show like things like fire, like a guy with like sparkles going everywhere, the beach, very difficult reflections with the sun hitting the waves and these kind of things. And that is really what they managed to do, because again, like I said before, like when you do your head movements, you get a lot of information from the reflection of light. And not being able to do that kind of like reduces the immersiveness of the experience, especially if it's a complex scene. But by recording multiple viewpoints that you can then go around into, not only feels more natural, but will also give that next level immersion kind of thing that we're looking for.
Yeah, excellent. And actually, like the Invisible Hours or whatever, I just saw in chat someone mentioning, Damien mentioned like a virtual whodunit. Like, what if you did, real actors, for instance? We take this whole thing that we would talk about with Tempest and other examples, and you apply this kind of technology once it's available. You'd be able to do something like that again, potentially just with that small range of movement, but you really feel like you were there. And those would be maybe not even virtual actors, maybe they'd be real actors captured again volumetrically, but then translated to you in 6DOF over the internet. So there's some pretty exciting concepts out there,
Yeah, interesting stuff. I'd imagine this is going to be like years ahead before we see some sort of major leaps and advancements in this tech, though, I'd imagine.
Well, it all depends again on like the groups that are working on this, and the amount of money that is being pumped into this. We all know that the more money that is being pumped into this kind of research, the more application potential and the more interest of the big brands that is in this kind of technology, the faster that this technology will be pushed forward. So yeah.
Nice. Well, thank you very much, Rowdy. I really appreciate your Rowdy science lessons. They're always super informative. Always kind of blows my mind a little bit, each time. But no, I really appreciate it. And the audience really like it as well. So thank you again.